The most complicated math has the most elegant solutions. Okay, we are looking at an example of an elastic collision in one dimension. And a thing to remember about elastic collisions is both momentum and energy are conserved in this collision. So the initial momentum will equal the final momentum, and the initial energy will equal the final energy. Okay? What we have in this setup is we have a purple ball with a mass equaling 2 kilograms, and it's initially moving at 5 meters per second. It strikes a green ball that is stationary. This green ball has a mass of 3 kilograms, and it has initial velocity of 0. Feel good? Okay. What we're looking for here is what are the final velocities of these two balls. So let's call this like a projectile and the target. So we're simply looking for the final velocity of the projectile and the final velocity of the target. We are first going to do this just using our equation that we have in our notes. And if you haven't seen this equation, please go check it out. It is super, super helpful. But then we'll come back and we'll actually work through this problem in a much longer format to show all the mathematics. Our final velocity of our projectile, according to the notes we last did, is the mass of this projectile, the initial mass of the projectile, minus the mass of the target, divided by the mass of the projectile plus the mass of the target, multiplied by the initial velocity that the one object has. And we can only use this equation because this green ball is stationary. So that this initial velocity here, that's going to be our 5 meters per second from our projectile. For our target ball, what's its final velocity, the green? Well, that, according to our equation, is going to be twice the mass of the projectile divided by the mass of the projectile plus the mass of the target, multiplied by some initial velocity, where that initial velocity was the initial velocity of the only thing that was moving, the purple ball. So if we go ahead and use these equations, and these equations like kind of came out of thin air for us, we can say this is equal to then 2 minus 3 divided by 2 plus 3 multiplied by that initial velocity, which was 5 meters per second. If we go ahead and put a lot of this together, we are going to get negative 1 over 5 times 5. The 5's divide out, and we quickly see that the final velocity of our projectile is equal to negative 1 meters per second. If we do a similar thing on the right-hand side for our target, we can say 2 times the mass of the projectile, which was 2, divided by the addition of the projectile and the target, that's 2 plus 3, multiplied by the 5 initially. What we get on this math is 4 over 5 times 5. The 5's go away, and we find that the final velocity of our target was 4, or positive 4, meters per second. So by using these two equations in our notes, we can quickly get an answer here. Now this is where we start taking the deep dive. If you want to, you can actually conserve momentum and energy and mathematically get these answers back. There's a lot of math and algebra, and we're going to get these same answers, but here's how we would do it. And this is what you would have to do if that green ball wasn't stationary and we didn't have these equations. The first thing we'd have to do is to conserve momentum. When we conserve momentum, what we are saying is that m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f, where 1 and 2 are the projectile and target respectively. In our setup, what we would have here is 2 times 5 plus 3 times 0, so that's going to be nothing, equals 2 times v1f plus 3 times v2f. I guess if you wanted, you could take 2 times 5 and make that 10. So let's just do that. And then let's just get rid of that 3 times 0 because it's just 0. So that's our conservation of momentum. The next thing we can do is we can set up our conservation of energy. In this case, we're on a flat surface, so there's no gravitational energies changing, and there's no springs, so there's no spring energies or elastic energies. There's just kinetics. So what we'd have here is 1/2 m1, so that's going to be 2, times v1 squared, so that's 5 squared, plus the initial kinetic energy of the stationary target, that was 0, so let's not even bother putting it. This is going to be equal to all of the final kinetics. So that's 1/2 the mass of the projectile, which was 2, and its final velocity squared, plus 1/2 times the mass of the target, which is 3, times its final velocity squared. A neat thing you might notice here in this green, or this final kinetic energy equation here, is that they all have 1/2, which means we can actually eliminate the 1/2 from the equation. We're just simplifying things a little bit. Now here's where we start getting into a pickle. For our momentum equation, we are missing this final velocity of the first object, the projectile, and the final velocity of the second object, the target. That's 2 unknown variables. That means we need 2 equations. Luckily for us, we have the momentum equation, and these 2 missing variables pop up in the energy equation as well. So with 2 unknowns, we have 2 equations. We can do a substitution method. But it's going to be long. First thing we're going to do is we're going to rewrite this momentum equation, but we're going to solve it for the final velocity of our projectile, okay? To do so, I need to subtract 3 times the target final velocity to the left. So I'm going to get 10 minus 3 v2f equals 2 v1f, and then I'm going to divide by 2 so that I can get just v1f. When I divide by 2 like this, I'm going to simplify. We'll see why it makes it a little bit easier later on. 10 divided by 2 is 5. And 3 divided by 2, I'm just going to say, is 3/2. But this equation is equal to v1f. Now I'm going to take that equation for v1f, and I'm going to put it into my energy equation for V1F. We see this is going to be slightly annoying because when we do this, we have to square it, which means we're going to have some foiling to do. So let's substitute these values in. So I'm just going to rewrite everything here. I'm going to have 2 times 5 squared, and that's going to equal 2 times, I'm going to put a big parenthesis here because I'm paranoid about parentheses. This is going to be 5 plus 3 halves V2F squared. And I've just been informed that I can't do basic math. This plus isn't a plus, it's a minus. Ugh. Get with it. Sorry about that. And then we have here plus 3 times V2F squared. Now, in this equation, we're only missing one variable, the V2F, so we can solve it. It's going to be a bit of a pain, though. And the reason being is this right here. This is a quantity squared. And since it's 5 minus 3 halves V2F, what we're really doing here is 5 minus 3 halves V2F times 5 minus 3 halves V2F. Which means that we need to FOIL this. We need to go like first, outer, inner, last, that whole thing. That's going to be kind of annoying to do, but it's what we have to do here. So we'll do 5 times 5 to get 25. When we do 5 times the negative 3 halves, we're going to get negative 15 halves, but then we're going to do that again for these inners here. So negative 15 halves and negative 15 halves put together is just going to be negative 15. So we're going to get minus 15 V2F. And then when we do our last, the negative 3 halves and the negative 3 halves, when they multiply together, we're going to get a positive. Negative times a negative is a positive. 3 times 3 is 9. 2 times 2 is 4. And V2F times V2F is V2F squared. Whew. So now what we have is the following. We have 2 times 5 squared equals 2 times 25 minus 15 V2F plus 9/4 V2F squared plus 3 V2F squared. Okay. Let's start simplifying this a little bit and try to put it into a nicer form. On the left here, 5 squared is 25. 25 times 2 is 50. And then I'm going to subtract that 50 over to this side. So I'm going to have 0 equals a bunch of stuff. And then here's the negative 50 I just subtracted over. I'm going to add that to the rest of this here in blue. And when I do this, I'm going to distribute this 2 throughout everything. Well, 2 times 25 is 50. And this is nice because negative 50 plus 50 is going to work each other away. 2 times negative 15 is negative 30 V2F. 2 times 9/4 is going to give me 18/4. So plus 18/4 V2F squared. And then I could write this as 3 V2F squared, but I'm going to have to combine these V2F squareds and these V2F squareds. And since I have this denominator of a 4th in the bottom, let's take this 3 and turn it into something over 4. And in this case, to make that common denominator, that's going to be 12 over 4 equals 3. So I'm going to get 12 over 4 times V2F squared. Okay, still churning on. Now, when we look at this, we're going to get the following. I'm going to write it so that the 0 pops on the other side. I've got negative 30 V2F plus 18 over 4 plus 12 over 4 is going to be 30 over 4. 30 over 4 is like 15 over 2. So we can say 15 over 2 V2F squared, and this equals 0. It will be easier if I don't have this half in the denominator. So I'm going to multiply both sides of my equation, all of this and the 0, by 2. That's like just multiplying by 1. Nothing has really changed here. But what it gives me is the following. It gives me now a setup I can write as 15 V2F squared minus 60 V2F equals 0. And at this point, this is starting to look like something we have solved before. When we were doing projectile motion and we had equation number 5 with the t squared in it, we had some setups that kind of looked like this. We could solve this as a quadratic, that is doable, but what we can also recognize is that the V2F, which is squared, and the V2F, they have a V2F in common. So I can pull one out. I can say V2F times 15 V2F, it's no longer squared because I pulled one of them out, minus 60 equals 0. Just like a quadratic, there are two solutions here. I'm trying to figure out values for V2F such that when we put them all together, they'll equal 0. Well, one of the values that I could pick is V2F equals 0, because 0 times whatever happens on the inside is still 0. But that's the trivial solution. That's the solution if they don't collide, or they haven't collided yet. I don't care about that solution. The whole problem is that the things hit each other. So let's ignore this outside trivial solution. Let's just solve this for the interior here. The 15 V2F minus 60 equals 0. If we want to solve this, we'll add 60 to each side. We get 15 V2F equals 60. And now we just divide each side by 15 to find V2F. And V2F in this case is 60 divided by 15, which is 4. 15, 30, 45, 60. And classically, because it's a velocity or speed, we get meters per second. That's the same value we found with our magic equation. This is the kind of work that we would have to do to get that equation back. If you wanted to find the final velocity of the first object or the projectile itself, that's fairly straightforward to do. We can take this value of 4 meters per second here, and if we go way back up, we could put it into this equation right here. This was the substitution equation. If we put 4 meters per second into this, what we get is 5 minus 12 over 2. 12 over 2 is 6, and that's going to equal V1F. 5 minus 6 is negative 1, which is exactly what we saw. So if you have scenarios where you're missing a lot of things and the objects are both moving afterwards, or the initial object isn't stationary, you have to do this. But if that initial object is stationary, you can use our magic equations and be quickly done like we've seen here. This is now finished. Until next time, adios and take it easy.